A group of scientists gathers at the La Jolla Laboratory of the Institute of Geophysics, University of California. Their discussion concerns the results of a unique experiment. They have been studying the passage of waves across the Pacific, identifying and following groups of waves all the way from their source in Antarctic storms northward to the coast of Alaska. Dr. Walter Munk, director of the laboratory, originated this study of energy, waves, and the sea. With his colleagues, he spent an entire summer tracking waves generated by the severe Antarctic storms. Waves that propagate across the entire Pacific, the largest body of water on our planet. Waves that are interrupted only occasionally by the upthrust of a lonely coral atoll. Waves that smash endlessly against the rock of high volcanic islands like Samoa. Waves which 10 days later die quietly on the beaches of distant coasts. The end of a journey half around the world. Modern technology and instrumentation made it possible to cope with the vast amount of data collected. The project required equipment for sensitive measurement and data analysis. The expedition used one of the most curious ships ever developed. Flip, a 355-foot floating laboratory that can stand vertically in the sea, and in that position, the most stable floating platform in the world. Dr. Munk's study, supported by the Office of Naval Research and the National Science Foundation, was most ambitious. This was the first time that men had simultaneously gathered precise and detailed wave data over global distances. The originator of the expedition recalls how the study began. Dr. Munk.
We have known for some time that Antarctic storms generate enormous waves which can be detected halfway around the globe. Although these waves become smaller and lose energy as they move away from the storm area, when they reach distant coasts, they are still detectable. We wanted to see if we could identify a train of waves from storms in the Antarctic region all the way to the beaches of Alaska. We particularly wanted to study the processes by which wave energy is lost. I had been under the impression that much of the wave energy would be scattered in the region of the equatorial trade winds and so prevented from getting to the North Pacific. The expedition, we hoped, would give us the first quantitative evidence to test this conjecture. The sea itself was our laboratory. Ocean swell, trains of waves moving across the sea, can come halfway around the world to deliver its power on the shore in the form of breakers. And here in the surf, the historic line of battle between land and sea, that power is immediately clear. Here the energy of the waves seems concentrated. A swimmer feels the power of the sea here. It pushes and pulls and can tumble him end over end if he is not strong enough to swim against it. But when a swimmer pushes out beyond the breaking surf, his water environment changes. Here the turmoil is left behind. Here he floats quietly, holding gently with the swell. The circular motion or orbital motion of his head reveals a basic fact about ocean waves. The water does not travel with the waves. The water does not stream towards the shore. This is clearly seen in a wave tank. There's virtually no flow of water in the direction of the wave. Only the wave form advances. The water particles move in nearly circular orbits. At the surface, these orbits have a diameter equal to the height of the wave. Beneath the surface, the orbits of the water particles become smaller. As a wax ball slowly sinks, it demonstrates the diminishing orbits of the water particles. The effect of the wave virtually disappears at a depth equal to 1/2 the wavelength. A submarine at such depth is hardly aware of the heavy waves on the surface. Water waves are characterized by wavelength, the horizontal distance from crest to crest, by height, the vertical distance from crest to trough, by period, the time required for two crests to pass a point. The velocity of a wave is determined by its period. Our study, of course, was concerned with real waves in deep water, waves at sea. Such waves hardly resemble the model waves, for they are of all sizes and come from all directions. They are mixed and piled atop one another in lovely confusion. Our job was to select from this confusion the particular waves we were interested in. We wished to identify them, to record and track them. To do this would require special equipment and analysis. At the La Jolla Laboratory, Frank Snodgrass was at work developing our instruments. The job was a tough one, to devise equipment that could extend our senses and measure waves a mile long and 1/10 of a millimeter high, waves completely beyond detection by unaided eye. The heart of our equipment was a device for transforming variations in water pressure into an electrical signal. This device, placed on the sea bottom, was to record waves passing above. A thin tungsten wire is mounted in a cylinder between a rigid base and a diaphragm. The wire vibrates. As the water pressure increases under a wave crest, the diaphragm is depressed, the tension in the wire is slackened, and the frequency of vibration reduced. The wire oscillates in a magnetic field inducing a fluctuating current. This electrical signal is amplified, transmitted, and recorded. The tape record is then a direct measure of the pressure at the sea bottom from which the wave profile can be calculated. The delicate wave sensor is housed in a sturdy brass cylinder to protect it from the sea. In the past, our data was visually recorded by wiggly lines on paper. For this expedition, the data would be recorded on punch tape equipment for direct input into a computer. I was frightened by the idea of using such fancy digital equipment on remote islands far from repair facilities. But I agreed it was necessary because of the large volume of data we anticipated collecting. The speed of the modern computer would allow us to get some results while the stations were in operation, to play things by ear, and to improve our procedure in the field. During our expedition, it would be winter in the southern hemisphere. Waves generated by severe storms in the Antarctic passed to either side of New Zealand and spread out in all directions across the Pacific. So we had a large area in which to choose locations for wave recording stations. The selection included a compromise among many factors. First of all, we preferred islands we could get to. Stations would have to lie on a great circle route so that we would all be measuring the same wave trains, and they should be about evenly spaced. I was particularly anxious to find a route including an island near the equator, for I expected a dramatic loss of energy in the equatorial trade winds. Many great circle routes were considered and many possible sites were discussed. Klaus Hasselmann looked into the problems of island shadowing. Islands cast shadows much as if the water waves were light waves. We wished to keep our recording stations out of any major shadows. Gaylord Miller dealt with the problems of near-shore refraction. As waves approach a shore, they feel bottom, are bent by the configuration of the underwater topography. We wanted as little refraction as possible in the area of our wave measuring equipment. At last, 6 locations were selected along a great circle route 10,000 miles long, stretching across the entire Pacific. At New Zealand, Cape Palliser Light, a rugged, storm-battered point where the first arrival of the great waves from an Antarctic storm could be expected. volcanic islands of Samoa, 2,100 miles to the northeast, where a favorable wave exposure was found along the exotic southwestern shore of Tutuila. 1,600 miles beyond, the uninhabited equatorial atoll of Palmyra, 2 miles in diameter, with no point of land more than 6 feet above sea level. In Hawaii, we selected Kewalo Basin in downtown Honolulu. This was our central wave station, easily accessible, and it served as headquarters for the expedition. To monitor the North Pacific, where there are no islands, the mobile island Flip was stationed at 45 degrees north and 150 degrees west. Her name is not simply a nautical joke. The letters stand for Floating Instrument Platform. At the end of their 10,000-mile journey, our waves would finally die on the beaches of Alaska, our final recording site. After months of preparation came the day when we were at last able to pack our gear and send it to the remote destinations by yacht, freighter, military, and commercial aircraft. At this stage, we were apprehensive. Would all of this gear bring back the answers we sought? There was only one way to find out. In Alaska, our recording instruments were to be housed in the Coast Guard station at Yakutat. A fishing boat, operated by an Eskimo crew, took Gaylord Miller out to the spot selected where the water depth was 60 feet, deep enough so that the waves had not yet been substantially affected by the bottom. The tough problem was to get the cable ashore. The line fired up onto the beach was used to pull the cable from the wave sensor to shore. The wave sensor, mounted on a quadrupod, was lowered into the sea and the spot marked with a buoy. The recording equipment on shore could now be connected. In Samoa, the problem of installation was simpler and warmer. First, we laid a cable from a nearby village to a rocky point. There, a narrow underwater crack in the rock with a sandy bottom was a naturally protected place to lay the cable. The cable would have to withstand a full summer of buffeting from the pounding surf. The wave sensor had been lowered into the water from an outrigger beyond the breakers. We had to hurry to stay with our schedule. Winter was descending on the Antarctic. Studying the weather maps of July 5th, Bill Powers noted a great storm building up south of New Zealand. This storm would impart energy to the sea and create the wave trains we wished to study. Cape Palliser, New Zealand, on July 6th, the waves from this storm arrived. The station had gone into operation just one day before. At last, our instruments could measure some real Antarctic waves. Frank Peterson, in charge of the New Zealand station, was pleased to note that the wave sensor was working smoothly. Each 2-second reading gave a sample of the wave height measured to the nearest 10th millimeter. We had all gotten pretty good at reading the tape code. It gave us the advantage of an on-the-spot analysis of the waves. This is a plot of the sea surface against time. The profile is irregular. A typical interval from one crest to the next is 16 seconds. This is the wave period. Knowing the wave period, we could predict the travel time of a wave group and estimate its arrival at the next station. The velocity and length of water waves is determined by their period. Long period waves are fast. These cross the screen in 5 seconds. Short waves are slower. These take 10 seconds to cover the same distance and are therefore traveling at half the velocity of the previous long waves. However, the velocity of a wave group is different from the velocity of individual waves. On the leading edge of a wave group, the first wave repeatedly disappears to be replaced by wave number 2. The wave group advances at half the speed of the individual waves. The wave front crosses the screen in 10 seconds. The individual waves, with twice the velocity, cross the screen in 5 seconds. Group velocity can be computed if the period is known. At New Zealand, the period was measured at 16 seconds. The corresponding group velocity was 27 miles per hour. In Samoa, it was the arrival of the wave group that interested us. We were not trying to identify individual waves. On July 8th, the waves arrived as expected. Here the waves were right on our doorstep. We lived in a Samoan folly on the edge of the village. The house was built entirely of coconut palm, an ideal place to work on waves. The house was open on all sides. It afforded lots of comfort and no privacy. To operate our recording equipment, we had taken along our own generator. As at all the stations, we recorded for 3 hours twice each day, from 4 to 7 a.m. and from 4 to 7 p.m. Each day we punched out 10,000 data points to be digested by the computer at home. We hardly ever missed a measurement. The equipment worked admirably, and my initial apprehension soon vanished. Data taking became quite routine. My wife and some of the Samoans learned to operate the recording equipment. Our measurements indicated some loss of energy between New Zealand and Samoa, but lots of wave energy remains. Preliminary analysis showed that the waves at Samoa were more regular than at New Zealand. This is because the long waves, which move rapidly, have separated from the short waves, which are slower. This is a phenomenon known as dispersion. To see dispersion, one can toss a handful of pebbles into a pool and watch carefully. As in full-scale storms, waves of all shapes and sizes are generated, and they spread out confusedly in all directions at once. As they leave the storm area, the waves begin to sort themselves out. The long waves move out fast, the short waves more slowly. Away from the storm, the confused sea has become swell. The waves are separated and regular. And as the distance from the storm increases, the long waves in front become even further separated from the lagging short waves. The wave train stretches out more and more. The further the group has traveled, the longer it will take to pass a wave station. The computations, taking dispersion into account, made it possible to predict not only the storm waves' arrival time at other stations, but also to estimate their duration. I went to Pago Pago to pass this information on by radio. Radio amateur Paul Hodges got us in touch with the other wave stations.
Good morning, Frank. Everything's fine, station going well. We're having a rather nice sequence of waves come in, which reached their peak probably early this morning, probably associated with the New Zealand storm.
Do you know what this means? With the duration...
I estimated the arrival of the storm waves in Palmyra on July 10th. I informed Gordon Groves in Palmyra that taking dispersion into account, he could expect the waves there to have a duration of 2 days. The disturbance had passed in a day and a half in Samoa.
And wondered if it looks like might be getting some good waves coming into Honolulu 4 or 5 days. Yeah, let's all see what can go.
In Hawaii, the same wave group will arrive on July 11th, and the waves should, because of dispersion, take 3 days to pass. Frank Snodgrass's calculation agreed with
If
mine.
it does come through, I'll let Flip know. I'll also wire Alaska and alert them all. How long ago was it that you talked to them?
So everyone could anticipate the arrival of the great waves from our first storm. At the same time, Frank Snodgrass had learned from New Zealand about the birth of a new Antarctic storm.
We have 40 to 45 knots of wind at latitude 64 and longitude 177 east. This is a mean wind.
The fresh storms building up in the Antarctic would happily provide an abundance of waves for us to measure throughout the summer and enable us hopefully to reproduce the results of our first storm. The kind of control plots we were making with the punch paper tape while on station were inadequate for detailed analysis. While the gathering of data continued, the paper tapes were regularly flown to La Jolla for computer processing so that Frank and Klaus could keep a running account of the experiment. In order to see our waves most clearly, we had decided to look at them in a special way. We programmed the computer to evaluate and plot out a spectrum of the wave data. A wave spectrum is a plot of wave energy against wave frequency. Energy is represented vertically and frequency is represented horizontally, with the low frequencies or long periods on the left, the high frequencies on the right. The arrival of the wave group from the Antarctic shows up as a distinct peak in the spectrum with a given peak frequency. Because of dispersion, the peak first shows up at the low frequency or long period end of the spectrum. These were the first wave arrivals from the storm. On later records, the peak gradually shifts to higher frequencies. These higher frequencies, or shorter waves, arrive later because of dispersion. After several days, the wave group has passed. The peak disappears. As our waves progressed northward, they encountered waves from local storms. The swell passed through these locally generated waves like ghosts and continued their journey towards Flip, virtually intact. Flip had arrived at her lonely North Pacific station on her first major assignment at sea. The wave sensor had been bolted to the hull of Flip and would reach the proper depth when Flip flipped. As the strange ship floods her ballast tanks and slowly tilts to her vertical operating position, all but 55 of her 355-foot hull sinks underwater to form a surprisingly stable base of operation. Flip is designed to heave up and down at a natural period which is longer than the longest swell. Consequently, she barely moves with waves, only 3 inches in a 30-foot sea. As she flips, the crew aboard shifts with her, walking now on what before were walls and rails. Jack Northrop operated the wave recorders aboard Flip while she was on station for a month. Wave measurements aboard Flip were comparable and in some ways better than those on land. Flip floated with negligible drifting, taking wave measurements for 3 hours, twice a day. After a 10,000-mile journey across the world's largest ocean, our waves, direct descendants of the waves born in the Antarctic winter, finally reached the shores of Alaska. Here, after their 2 weeks' journey, they finally die on the gently sloping beaches. The energy which had traveled across half the planet is at last expended in the breakers. The Alaskan station was operated by Gaylord Miller. He was the only one of us who sometimes met a bear on his way to work. The Coast Guard station gaze recorders took a twice-daily record, the last look at our waves. It was here that our data would, we hoped, tell us how much of that energy had been lost in transit. When at the end of the summer we finally returned to California, we had amassed 10 million data points documenting waves from 12 major storms. A person with a desk calculator would have taken 2,000 years to convert this data into a meaningful picture of what happened. With a high-speed computer, our analysis was finished within a week of the end of the expedition. Bill Powers plotted day-by-day spectra. Plotting the spectra for the storm waves, we see a sloping ridge showing again the early arrivals in the low frequencies, followed on subsequent records by higher frequencies. This can be seen more clearly in a three-dimensional model. Here's the wave spectrum at Samoa for the morning of July 26. The peak indicates the earliest arrival of the wave group from our first storm. 12 hours later, the peak is bigger and has shifted to a higher frequency. Frequency increases from left to right. The same thing happens again with later spectra until the peak diminishes and disappears. The spectra for the entire wave group at Samoa show the storm as a slanting ridge starting at the low frequencies and ending in the high frequencies because of dispersion. The duration of the wave group at Samoa was 3 days. As we go to Palmyra, we see the same storm ridge, but it is more slanting because dispersion has stretched the wave train. Accordingly, the duration of the ridge has increased to 5 days. The data amassed from station to station shows that for this storm we have succeeded in characterizing the wave climate across the entire ocean. On the basis of observations in Samoa, we could predict surfing conditions in Hawaii 3 days in advance. Our principal aim, however, was to learn something about the attenuation of waves, to compare the energy of the ridges from station to station. We found that the high frequencies were reduced quite a bit between New Zealand and Samoa, but not the low frequencies. However, attenuation from Samoa all the way north to Alaska is surprisingly small for all frequencies. There's no appreciable loss of energy across the equator, so my original conjecture about severe equatorial attenuation is wrong. Our observations and calculations now lead us to the following conclusions. Attenuation is largely the result of interaction between waves from the same storm. The interaction is weak once waves are well sorted by dispersion, and this explains why the attenuation is initially large and then negligible. The interaction is weak at low frequencies and strong at high frequencies, and this explains why only the high frequencies are attenuated. These observations are in general agreement with theory, and we are now one step closer to predicting waves from distant storms. In talking things over, we're pleased with how well these storms were documented by the experimental program. We are somewhat disappointed that the measured attenuation varied considerably from storm to storm, but this should be no surprise, for in nature, no two storms or no two waves are ever alike.